So in this video I want to discuss the idea of even and odd functions, and I'm also going to talk about the graphs of such functions. And the basic idea of an even function is that if in the argument of the function you replace the variable, in this case x, by minus itself, and if you get the function again, so f of minus x is the same as f of x, we say that the function is even. Similarly, if we replace in the argument the variable by minus itself, so here we have f of minus x and we get minus f of x, we say that the function is odd. And it is not the case that all functions are even or odd. Sometimes if you replace the variable by minus itself, we have f of minus x, it is neither f of x and it is also not f of minus x. And in that case we simply say that our function is neither even and it's also not odd. So what I want to do on the next slide is to look at a couple of examples of functions which are even, odd and neither even nor odd. So on this slide I'm going to work through 5 examples of functions. F of x is x squared, f of x is sine of x, f of x is e to the x, f of x is 1 over 1 plus x, and f of x is 1 over 1 minus x squared. So let's look at the first example. So let's look at f of x is x squared. The easiest way to work this out is to consider the function evaluated at minus x. So here we're going to have minus x all squared. And that of course is x squared, which is the function evaluated at x. So we conclude that this function is an even function. For our second example, the sine of x, in a similar way, we realize that our function evaluated at minus x, in other words, the sine of minus x, is minus the sine of x from the symmetry property of the sine function. So this is minus f of x, and this tells us that our function is an odd function. Our third example is the case of e to the x. Our third example is the function e to the x. So again, what we look at is our function evaluated at minus x. So that means in our function e to the x, we replace x by minus x. We have e to the minus x. This means 1 over e to the x. And 1 over e to the x is not the same thing as e to the x, and it is also not the same as minus e to the x. So it is not e to the x, and it is also not minus e to the x. So our function e to the x is neither even nor odd. So neither even nor odd. Our next example is 1 over 1 plus x. So here our function evaluated at minus x is 1 over 1, and now we replace x by minus x, so we just have 1 over 1 minus x. And again, this is not the same as 1 over 1 plus x, and this is not the same as minus 1 over 1 plus x. So again here we have a function which is neither even nor odd. And our final function on this slide is 1 over 1 minus x squared. So f of minus x is 1 over 1 minus, this is minus x squared. And just as in our first example at the top, minus x squared is plus x squared, so we're going to have 1 over 1 minus x squared. So this is 1 over 1 minus x squared. This is our original function, f of x. It's exactly what we started with. So therefore we conclude that this is an even function. So I hope we've seen how it's possible to check whether a function is even or odd. You just take the variable in the argument, replace it by minus itself, and see what happens to the function. And on the next slide I'm going to write out 2 more examples for you to work through. So we've got 2 exercises here for you to work through to verify whether these functions are either or odd or neither. And what I suggest you do is write them down, check, pause the video, see what you get, and then play the video again and we'll see. Okay, so welcome back. So what we're going to see with the first function is this is a function of a variable t, and if we want to see if it's even or odd, what we need to consider is the function evaluated at minus t. So this is the cosine of minus t, and by symmetry the cosine of minus an angle is the same thing as the cosine of the positive angle. So this means that this is indeed an example of a function which is even. For our second case, where we are looking at a function t multiplied by the cosine of t, what we see is that our function evaluated at minus t is going to be minus t multiplied by the cosine of minus t. So this is minus t, and then the cosine of minus t, as we just argued above, is the same thing as the cosine of t. So this means that we are going to get here minus t from the first factor multiplied by the cosine of t. So we conclude that this is the original function multiplied by a minus sign overall. So this is an example of an odd function. And it's worth noting that quite generally, if we have 2 functions, if f of t and g of t are, let us say, both odd, then f of t multiplied by g of t will be even, and the proof of this argument is we take f evaluated at minus t multiplied by g evaluated at minus t. Since these are both odd functions, f of minus t is minus f of t, and I'll put this in brackets, and then this is multiplied by g of minus t. Because it is also an odd function, we get minus g of t. So when we multiply these brackets out, we're going to get 2 minus signs, one here and one here, multiplying together. So we're going to get overall plus f of t times g of t, and that's what we expected. This is clearly an even function. Now, this is also true for the ratio of 2 odd functions, and similarly an odd function multiplied by an even function is going to be odd. So let's look at an example of this on the next slide. So the example I want to look at here is the tangent function. I'm going to be calling the variable here theta. So the tangent of theta is the sine of theta divided by the cosine of theta. So therefore, if we want to see whether this is an even function or an odd function, we want the tangent of minus theta. So this is the sine of minus theta. We divide by the cosine of minus theta. The sine function, as we have already argued, is an odd function, minus the sine of theta. The cosine function is an even function. So therefore we see that the tangent of minus theta is going to be, and here we have minus sign divided by a plus sign, so we get minus, and here we have sine of theta divided by the cosine of theta, which is the tangent, so we get minus the tangent of theta, so therefore the tangent function is an odd function. So, what I want to talk about on the next slide is about the graphs of even and odd functions, and really it's the graphs of even and odd functions that make this whole division of functions into even and odd functions, or neither, particularly useful and interesting. So here we're going to talk about the graph of an even function, and let's just recall an even function is a function such that if in the argument you replace x by minus x, you get exactly the same value. In other words, it doesn't matter whether you have a minus sign here or a plus sign, you have exactly the same value for the function. So if on the axes that I've drawn here, I sketch f of x for some positive set of values of the function, so let me, for example, sketch this for the cosine function as an example, but it really doesn't matter what it is, so I'm just going to label it y is f of x. Because it's an even function, if I take the value here, it's some value of x, and I then go the same distance here to minus x, I must have the same value for the function. So the function is going to be on this side a mirror image of the function on this side. So I can take the function and I rotate it about the y-axis, I just flip it over and I get a perfect mirror image. If I was to imagine taking this screen, cutting it here and folding it along the y-axis, I would get this to match up perfectly. So the graph of an even function is, we conclude, this is the important moral, that the graph is mirrored about the y-axis. And this makes it easier to sketch such graphs, and it also has important implications for definite integrals. But in particular, just for curve sketching, if you can sketch it for x greater than 0, for x less than 0, the graph is immediately given to you. You just have to make your mirror image. So on the next slide, I want to talk about odd functions. So on this slide, I want to talk about the graphs of odd functions. And an odd function, we recall, is a function such that if you replace in the argument x by minus x, you get the same function back but multiplied by a minus sign. Now, there is a special case that I think is very important to think about, and this is when x is equal to 0. So note, if x equals 0, f of minus 0, which is of course f of 0 because 0 is equal to minus 0, must also equal minus f of 0, where for this last step what I'm using is our inequality here. If I put 0 in here, here I have f of minus 0, which is 0, so f of 0 must be minus f of 0. And if we have this relation, there are only two possibilities. The first possibility is that the graph might pass through the origin. After all, the only thing which is equal to minus itself is 0. So that's one possibility. However, another possibility is that the function may not exist at 0. So the moral here is either our function passes through the origin, or f of 0, our function at x equals 0, does not exist. So on the next slide, I want to just draw such axes again and give a couple of examples of each and talk about what the symmetry property looks like in terms of making mirror images. So, as I just said, what I want to do now is look at graphs of odd functions fulfilling this condition by definition, and either our function passes through the origin, and an example of that would be perhaps a function that looks like the sine function, something like this, and we know that this is roughly what it looks like, so this is y is f of x, and if we know that our function looks like this for positive x, what we have to do is to realize that if you go from, say, to here, some value of x, to a similar negative value, so you just replace x by minus x, you're going to have whatever the value of the function was multiplied by a minus sign. So you take the curve, you mirror it about the y-axis, and you then multiply it by a minus sign, and that means you mirror it about the x-axis. So first mirror, second mirror. And what that's going to give us is a graph that looks something like this. So this is mirrored in a two-step process. So mirror first about, say, the y-axis, and then about the x-axis. Alternatively, it does exactly the same job. You could mirror it down here about the x-axis and then mirror it about the y-axis. It's completely a matter of taste. So, if we know what the graph of an odd function looks like for positive x, we can immediately write down what it looks like for negative x. This is a function which, as you can see, passes through the origin. On the next slide, I'd like to draw the graph of an odd function which does not exist when x is equal to 0. So, the example I want to look at on this slide is the graph of the function 1 over x. It's clear that this function does not exist when x is equal to 0. This function does not exist at x equals 0. We'd have 1 over 0, which diverges. And it is also odd. So it is an odd function. F of minus x is equal to minus f of x. 1 over minus x is minus 1 over x. So 1 over minus x is equal to minus 1 over x. That shows us that we have an odd function. So let me just draw the graph. I draw the axes, x and y, and I'm going to draw it first of all for positive x. So we've seen already that the y-axis is an asymptote. As x approaches 0, 1 over x, if x is positive, it's positive, and as x approaches 0, it's going to become extremely large. As x becomes large, 1 over x is going to become small, so this curve is going to have a shape something like this. Y is 1 over x. This is what it looks like for positive x. To get it for negative x, we can flip it to here, so we'd have something that looks like this. And then we can flip it about the x-axis, so the curve that looks like this, here goes to here, up here goes to down here, and we're going to get a curve that looks something like this. So this is, again, an odd function, and the behaviour for x less than 0 is dictated by the behaviour for x greater than 0 and given by the symmetry. The rotate to here and to here, or, if you wish, rotate first to here. You'd have a line like this, and then you flip it about the y-axis and you would get this curve. So, what I hope we've seen is that if you start off and can analyse that a function is even or odd, it can make it easier to draw its graph. It can also have implications for definite integrals. And on the next slide, I'm going to prove a final result about even and odd functions. So I want to conclude the video by pointing out that any function may be written as the sum of an even function and an odd function. So to do that, let's just give our function a name. I'm going to call it f of x, and I'm going to say that I'm going to write it as f of x plus f of minus x, all divided by 2, plus f of x minus f of minus x, all divided by 2. And if you look at that, you'll see we have f of x over 2 plus f of x over 2. So the 2 halves will give us 1 whole, f of x. But we also have f of minus x over 2 and minus f of x over 2. So those terms will cancel. So all we've done is we've written f of x in this way. This is an algebraic equality. But once we do that, we then notice that this tells us that f of minus x is f of minus x plus f of, and now here minus x becomes f of minus minus x, which is f of x. So the 2 minus signs here are going to give us f of x over 2. So our first term that we've written here, if we evaluate our function not at x but at minus x, gives us this, and we notice that this is exactly the same as the term above. We've just swapped the order that we write these things in the sum. Similarly, for the next term, we have f of minus x minus f of, and now again replacing x here by minus x, we have minus minus, gives us a plus. So this is f of x all over 2. So therefore f of minus x is f of x plus f of minus x over 2. So that's just this first part. And then for the second term, we have minus f of x minus f of minus x all over 2. So all I've done here is I've taken the terms above, I've swapped the order, and I've brought out an overall minus sign. And again, this term here is exactly the same as this term here with a minus sign in front of it. So comparing our result for f of minus x with f of x, we see that we can write our function f of x as this plus this. That was an algebraic equality, and we've seen that this part here is even, because if you replace x by minus x, you get exactly the same thing. And this term here is odd. You replace x by minus x in here, and you get the same thing but with a minus sign in front. So we see that this is even and the second term is odd. So in other words, it's always possible to take a function f of x and write it as a sum of two terms. We don't know anything special about this function to do this. This is just algebra, and we've seen that this part is even and this part is odd. So we can always write any function as a sum of an even function and an odd function in this way. And that concludes this video.